Hello everyone, in this video I'm going to go over the derivation of the equation of trajectory. That is, writing y, the height, as a function of x, the displacement from the origin in the horizontal sense. If at any point we consider the particle that's been launched at a speed u at an angle theta to the horizontal, if we assume that we're not acted on by any air resistance, the only force will be the weight, which will act vertically downwards. So as a result, the horizontal speed will not change. If we take and make a vector triangle from the initial velocity, I'll draw that here. We have a triangle that's angle theta here, hypotenuse is u, and we want to resolve this to gain our initial vertical velocity, which is this distance, and our initial horizontal velocity, which is this distance. We give these u of y and u of x, and just by using trigonometry, u of y is u sine theta, and u of x is equal to u cos theta. And because of the weight acting only in the vertical direction, if we consider the horizontal sense, this will not change. So we can use speed equals distance divided by time to relate speed, distance, and time. So for the horizontal, speed, which is u cos theta, is equal to distance travelled, which is in a horizontal sense, so that means x, divided by time. If I rearrange this for time, we end up with t is equal to x divided by u cos theta. And we're going to use this extensively for the derivation. Okay, what about the vertical motion? Well, if I take that down here in a different colour, in this case we do have a weight acting, we do have a force. So according to Newton's second law, we are going to experience an acceleration. And what is that acceleration? Well, the magnitude of the acceleration due to gravity close to the surface of the Earth is g, which has a value of 9.81 meters per second squared. But because of the way we've defined our axes, we've said that y increasing is vertically upwards. So as the acceleration points vertically downwards, acceleration is going to be minus g. We mark that with a line with two arrows. That's minus g. So considering the vertical motion, we can use our Suvad equations to relate y, the height obtained, and time. And that's in the form of s is equal to ut plus 1/2 at squared. And if we apply what we currently got to this formula, s is now no longer s, but it's y, the vertical height, is equal to u, which is the initial speed, but it's not the initial speed along this vector, it's in the vertical sense, which is u sine theta here. Now instead of t, I'm going to replace that with this, what we rearranged from the horizontal motion. So we're going to times that by x divided by u cos theta. For the next term, we've got acceleration is not positive, it's minus g from our sign convention. So rather than plus, it's going to be minus. Acceleration is g. And we've got t squared. Well, t squared is just this squared, which is on the top gives us x squared. We've got the 2 from the half, and then we've got u squared cos squared theta, just squaring that term there. And if we tidy this up a bit, cancel the u's in the first term, and recognise that sine theta divided by cos theta is tan theta, we end up with our equation of trajectory, which is y is equal to x tan theta minus gx squared divided by 2u squared cos squared theta. And this is our equation of trajectory. So given a value of x, which is our distance from the origin in a horizontal sense, we're able to obtain our y value. Now, are we happy with this? Well, does it make sense that this is an x term, an x squared term even? Well, we have a parabola here, we have a curve. So we were expecting definitely a squared term here, so we're reasonably happy with this. But we'll go on to justify our expressions for other things, and maybe I can convince you that this is definitely a sound formula. Okay, so there's two things we generally want to do with trajectories. First of which is to find the range, and that is defined as the distance from this point to this point, or the distance in the x direction. So let's do that first. How can we find that point using this formula? Well, the first thing to recognize is due to our axes, the way we've defined them, this point will be at the point y equals 0. So if we substitute y equals 0 into this formula and solve for x, we will obtain this point. So if we do that, we end up with x tan theta is equal to g x squared divided by 2u squared cos squared theta. That's just making this 0 and taking this term over to the other side. Now I'm going to divide by 0. Sorry, not divide by 0, divide by x. And we're going to assume here that x is not equal to 0. We do not want this here. We don't want this trivial solution because this will provide us x equals 0, which is it's kind of pointless for our situation. We want to find this point here. So cancelling that x, we're well justified. So if we rearrange this for x, we end up with x is equal to 2u squared cos squared theta times by tan theta, just taking this term up, and then divided by g. Now, cos squared times tan theta, well, tan theta is made up of sine theta divided by cos theta. So if we write that as that, we'd have sine theta on the top and cos theta underneath. So I'm going to cancel that cos with this other cos. So we end up with 2u squared sine theta cos theta divided by g. And from your double angle formula, you should know that 2 sine theta cos theta is sine 2 theta. So that can be written as u squared sine 2 theta divided by g. Okay, now are we happy with this? Well, does it make sense that if we increase our speed that we launch at, we go further? Well, yes it does. Does it make sense that if we increase the gravitational field strength, that we don't go as far? Well, again, yes. To justify this sine 2 theta, why is it sine 2 theta? Well, the maximum value for sine of some angle is at sine of 90 for our first solution. So what we're saying is, to get a maximum for this, we say that 2 theta is equal to 90 degrees. Because sine varies from +1 to -1, and we want to get +1 for our maximum. So we can say that theta for our maximum value is 45 degrees. Now again, does that make sense that we travel the furthest distance if our angle is 45 degrees? Well, yes, it does. If we pointed this vector vertically upwards, the particle would go up, turn around and come back down again. And if we pointed it horizontally, if it wasn't allowed to roll, this ball wouldn't travel anywhere. So our maximum range is obtained at an angle of 45 degrees halfway between. So we're happy with this. But what about finding this height, the maximum height obtained? That's the other thing that we normally want to do. Well, first of all, I want to find this distance here, this x distance. There's two ways we can do that. If we can see that this is symmetrical about this line, which is our maximum point, because it is a parabola, and say that the distance from here to the halfway point is exactly halfway between here and the end point, so we can just divide this distance by 2. Or, if you don't trust me, if you take the derivative of this expression, and I'll do that down here, if we take dy dx of this expression, we end up with dy by dx is equal to, if we differentiate x tan theta with respect to x, not with respect to theta, we just end up with tan theta. Tan theta is just a number. And if we differentiate the second term, we end up with minus gx divided by u squared cos squared theta. The 2, when we differentiate x squared, we get 2x. The 2 is cancelled with the 2 underneath, so we end up with this term. Now, what can we do with dy dx to find this point? Well, at dy dx, dy dx represents the gradient of this curve. And at this point, if we draw a tangent to the line, you can see that the gradient of that is 0. So dy by dx at that point is 0. And so what we can do is we can set this expression equal to 0. So we end up with gx divided by u squared cos squared theta is equal to tan theta. Setting this to 0 and moving the other term over. We multiply u squared cos squared theta up and divide by g. We end up with x is equal to tan theta times by u squared cos squared theta divided by g. Now this is exactly the same as this expression, apart from we've got half as much of it. So this is equal to half of our result that we had up over here. So you should have trusted me. We end up with u squared sine 2 theta divided by 2g. So yes, we have justified that this x distance here is equal to half of the x distance from here to here, the range of the expression. But what about calculating this height? Well, now we have a value of x, it's just a matter of substituting this value of x into our expression to get a value of y. So if we do that, we end up with y is equal to x tan theta. X is now this, so it's equal to u squared sine, and instead of sine 2 theta, I'm going to write this as 2 sine theta cos theta. It's equivalent, and it just makes it a little bit easier for doing the manipulation. So this ends up being 2 u squared sine theta cos theta divided by 2g. Again, we're going to cancel the 2's here and here, times by tan theta, because this was our x value, if you remember. Now if we look at our next term, we end up with minus g over 2u squared cos squared theta times by x squared. So minus g divided by 2u squared cos squared theta times by x squared. Well, if this is x, then x squared is just a matter of taking the product of this, which is going to be u to the 4th power times by sine theta, sine squared theta, cos squared theta, divided by 4g squared, squaring this term underneath. If we actually, sine 2 theta is 2 sine theta cos theta, so we're going to have an extra 4 coming out the front if we square that too. Sorry for that. This 4 will cancel with this 4. And then if we just write this out again neatly now, we end up with, on the left hand side, we have u squared sine theta cos theta tan theta divided by g. And if we deal with this on the right hand side, well, we have cos squared theta here, and that's going to cancel with that cos squared theta here. We have u squared theta here, so that's going to cancel with the u to the 4th power to give u to the 2nd power. So this is ended up being minus g u squared sine squared theta divided by g squared. Well, there's 2 from this 2 over here. This squared cancel with this g. Sine theta cos theta tan theta. Well, tan theta is sine theta divided by cos theta, so that cos theta is going to cancel with this cos theta, and the sine is going to end up being a product with this sine. So we're going to end up with u squared sine squared theta divided by g minus u squared sine squared theta divided by 2g. So our final term is going to be equal to this, subtract this, which is u squared sine squared theta divided by 2g. And so again, does this make sense? Well, of course, if we increase the speed, we're going to increase our height that we travel at. If we increase gravity, we're going to decrease the height that we obtain. And what about this sine squared term? Well, the difference between sine squared and sine is that sine squared is steeper. And so that means we're going to fall away from our maximum value quicker. But still, we obtain a maximum value for sine squared theta when theta is 90, which kind of makes sense. If we point our initial vector straight upwards, it's quite obvious that we're going to reach the highest height from this trajectory. Okay, thank you for watching the video, and I'll see you next time.